So the topic today is an application of Hartree-Fock theory, and it's an application to a system which has been widely used in solid-state physics. It's been extremely successful in explaining conducting properties of electrons in metals and what's called semi-metals. On Friday, on the other hand, we will just spend the rest of the day, or all the hours which we have, to discuss the midterm. But anyway, feel free to ask questions during the breaks now and so on. Now, one of the reasons why I want to bring up the electron gas, it's not only because it gives us analytical solutions to a many-body problem. It gives us analytical expressions for the Hartree-Fock single particle energy. And it gives us also analytical expressions for the ground state energy when we have a Hartree-Fock wave function. And this is a pretty unique situation because there are not many physics cases where we can extract analytical solutions. So this is something which you might call a textbook example, and you will find it essentially in all textbooks on many-body physics. And I thought it's, it's part of the many-body problem to actually have gone through the electron gas. And I think one would be a little bit, what's the right word for it? It's as if part of the culture of many-body physics is missing if we haven't done the electron gas. And it's also a case which is extremely useful because some of the technologies or the techniques which are being used are things which you will encounter in many other calculations. In particular, when you run calculations for these type of systems, when you want to do this computationally and go beyond the Hartree-Fock calculation, you would use this way of discretizing everything in terms of momenta, and you would put particles in a box with periodic boundary conditions. And that's a way by which you would simulate infinity. And then you can make this number of particles larger and larger. And then since you have the Hartree-Fock results, you can perform a Hartree-Fock calculation, a simulation of it. And then you can increase the size of the number of particles and see if you recover the infinite limit result. So today we're actually going to obtain what we will call the thermodynamical limit for the energy. That means that we have an infinity of particles. But when you run actual calculations, you will always be limited by a given number of particles. So it's not only an academic exercise, it serves also many useful purposes when you are mounting a many-body calculation for such systems. Such systems function also as a benchmark for many-body theories. One of the problems in standard many-body theories, whether you do Green's functions, or you do copper cluster theory, or many-body perturbation theory, is that you will never get the proper result which you would get from Monte Carlo calculations. So Monte Carlo calculations stand for a kind of benchmark for these type of systems. And this is because we have the long range of the Coulomb interaction, which means that there are specific degrees of correlations which have to be summed to infinite order. And you will see when we now discuss other many-body techniques that there will be problems if we deal with many-body perturbation theory. If we go to second-order many-body perturbation theory, the Coulomb interaction will give a divergent contribution. So it's an extremely useful system. And as we say here, so I'm just going to give you some of the basic background before we move on. So it's perhaps one of the few realistic systems which allows for analytical solution to Hartree-Fock equations. And there are also some kind of tricks there which are extremely useful to know about. And system of electrons is a system of electrons that is not influenced by an external force, except by an attraction which is produced by a uniform background of ions. And we are going to deal with that one. And what happens in this case is that this uniform background of ions will subtract exactly the direct term in the expectation value of the energy. So that means that we're only left with the exchange term for the energy. Now, this energy here, which you will also have an analytical expression for, is something which forms the basis for the first approximation in density functional theory. So some of you may have taken a course in density functional theory or studying density functional theory, and there you probably heard about the local density approximation. This is something you can derive from the electron gas here. So it's an approximation which comes from an infinite system, and it's used as a starting point for solving the mean field equation for density functional theory. So, and this is something we will discuss a little bit more in detail next week, the link with density functional theory. And typically what you would do now is, after they assume that this is the ions, they just form a uniform background. So instead of you having an atomic nucleus, which attracts an electron in, let's say, helium or neon or whatever kind of atom we are looking at, we now have a background of ions, which then provide a kind of uniform distribution of positive charge. So you can think of particles moving on top of some kind of uniform distribution of positive charge. And the system as a whole then is neutral because the charge from the ions balances the charge from the electrons. So the system is assumed to be neutral. And then you assume that you have a given number of electrons. This is the way you started. And then you let this number of electrons go to infinity. And this is typically set up in a box of a given volume. And this box with a given volume and the number of electrons define a density. As you know, the number of particles divided per volume defines a density. And this is a typical kind of quantity which is then used to relate to experimental results. Because the density can then be transformed into interparticle distances. And there are benchmark calculations for many body theories, which people believe are the best possible calculations you can get. And these kind of benchmark calculations were run by people like Zeppeli and other people. And I should say that we recently, this is a small digression, it's a propaganda for what I've been doing lately. We have actually used neural networks and we get a variational minimum, which is better than the benchmark by Zeppeli and company for the electron gas. So neural networks seem to catch a lot of the information of the wave function, which many of the traditional methods cannot. So this is just some small propaganda for that. And in dimensions as well, you have analytical solutions for the Hartree-Fock equations. You cannot solve the problem in one dimension because there is no 1 over r, where r is the interparticle distance, divergence in the kinetic energy. You only get that term when you take it to this two-dimensional case. And that 1 over r term cancels the divergency in the Coulomb interaction when the particles are getting close to each other. And that means that the wave function has to have a shape which goes like e to the plus the relative distance, the exponential. Yeah?
The number of electrons go to infinity.
Yeah.
What is the physical range behind it? Just that, in a box that it can be so many electrons.
Yeah. So what you actually want, this is a way to simulate infinity, because you set up the calculation with a finite number of electrons, but then you want the calculations in the thermodynamical limit. So in our case, the calculations here will be done at temperature equals 0. But still, when you think of an infinite system like this, this is an infinite homogeneous system. And you think of that system as a system where you have an infinity of electrons. And there is also a lot of, interesting results here. And one is a phase transition, which you have in 2 dimensions and also 3 dimensions. So the electrons can become very localized. So what happens is that they lose kinetic energy. So you can make the system, if you think of a harmonic oscillator potential, and the electrons are trapped in a harmonic oscillator. So this is perhaps the simplest case to think of. And when you make the harmonic oscillator very wide, the harmonic oscillator energy, which consists of kinetic energy of the system, plus the harmonic oscillator potential energy, depends on h bar omega. Omega is the oscillator frequency, multiplied with some constants. When you make the well wide, then the oscillator frequency goes to 0. And what happens then is that the contribution to the kinetic energy goes to 0. But what happens in that specific case, and this is counterintuitive, because the Coulomb interaction, the expectation value of that one is also small, but it is more important than the single particle piece. And when the system becomes dilute, the well becomes very wide, correlations become even more important. And that's due to the long range of the Coulomb interaction. So it's a balance between expectation value for the kinetic energy and the harmonic oscillator energy and the Coulomb interaction. If you look at this as an idealized system. So it's a very interesting case because that translates into a transition into a crystallization, which is called a Wigner-Seitz crystallization. And experimentalists are actually studying this, and they can see that the electrons become more and more localized. So obviously everything within Heisenberg's uncertainty principle. So they become more localized and correlations become more important. And the correlations are important due to the long range of the Coulomb interaction. So this thing with the long range is a little bit important because it's something which now also kicks into the electron gas calculations here. So the way we are going to look at this system is now in terms of first our set of plane waves function, which are normalized to a box volume. And we have a box of length L, and we are going to let this L go to infinity because we are going to make this box larger and larger. So it's the system which we are going to look at now is a system where we look at the energy per particle, because the energy is normally an additive quantity. So the more particles you have, the more energy you add, which means that if you were to calculate the total energy for a system where you have an infinite number of particles, the energy would go to infinity. However, we divide with the number of particles, so we're going to look at the energy per particle. That's the quantity we will take a look at now. And what I'm going to do now after these introductory words is actually to switch back to the whiteboard and just slow down the pace a little bit and go through the technicalities which we need to look at, if that is okay. So this was just to give you a kind of overarching motivations. There are plain, pure theoretical approaches here which are interesting to look at. The way we study an infinite system or a huge system. And at the same time, the approach you get, they can be directly linked with experiments which are done on semiconductors. So for those of you going into solid state physics, this is a system of great interest. And it has been studied for 50, 60 years, actually, or even more. Any questions so far? None, okay? Okay. So it's part of the, also of the kind of education in many-body physics. So let's switch back to the whiteboard and go through the calculations here and see if we get time to get through the calculations of the Hartree-Fock energies. And then next week, we will derive the total ground state energy as well. So the model which we are having is a model where we assume, so let's now assume now, this is the electron gas. And we are going to look at the case in 3 dimensions because that's the one which you will encounter in essentially all textbooks. So what we are assuming now is that we have a uniform distribution of charge from the ions. And I'm coming back to the way we model that one of ion charges. So we have a homogeneous distribution of ions, of positive ions. So that gives a positive background charge. And then the next case is that we have n, and I'm just going to use n instead of putting a subscript e. So we have n electrons, in a cubic box. And these electrons have a side, so this box has a side L, and we're going to let this L go to infinity with side L. This is the side. And volume, which obviously has to be then equal to L cubed. L cubed. And that gives us a density rho, which is given by the number of electrons divided by L cubed. So what we are going to set up now are the Hartree-Fock equations on integral form. And the reason for why we are going to set it up on integral form is because we are going to run these manipulations in what we normally call coordinate space or first quantization. So let's now remind ourselves of the Hartree-Fock equations in first quantization or in coordinate space. So I'm just going to write it like this in coordinate space. And these are the equations which we're going to use in order to derive the Hartree-Fock energy first. And then when we have the Hartree-Fock energies, we will move on to calculate the energy for the interacting case. Can everybody see well here, the screen? Okay. So if we now remember the equations, I'm going now to just write the kinetic energy. I'm going to use a shorthand for that one. So I will call that for T of X. And this doesn't, X is now a container for both the spatial degrees of freedom and the spin degrees of freedom. But we know that this one acts only on a single particle. So this is just 2 divided by m. But I'm just going to use T of X here as a symbol for it. So if I look at the equations then, what I have is a T of X plus a U of X. And this U of X is going to be the uniform charge from the background ion. And we then have a new term, which we, in coordinate space, called for the Hartree-Fock. This is just a Hartree-Fock term, which I'm going to call for U1. And I will set up what it means. And this is multiplied with the state we are looking at, which now depends on some quantum number alpha of X. I'm not putting vector signs on the X's, but X is now a 3-dimensional coordinate plus spin. And I will specify that just in a moment here. And then there is a new term here, which is the one which comes from the exchange part. So I'm going to set that up. So this is given by an integral over dx prime. And then I'm going to write up this 2 EU2 Hartree-Fock. And this depends on X and X prime. And then this alpha, which we have here, depends now on X prime. So this is the non-linear part of the Hartree-Fock equation. This is actually the exchange term. So we wrote this in the very beginning, but we never used it since we are so obsessed with second quantization. But in this case, it's actually useful to go back to the equations in first quantization. So let me just write down these terms for you. So this U1 Hartree-Fock of X is something which is normally called the U Hartree, and that's the way we called it earlier. And in this case, what we have is a sum over the states below the Fermi level. So we're going to have a sum over alpha prime, which is less than or equal than Fermi. So these are the states below the Fermi level. And then we have an integral over dx prime. And then we have the state phi alpha of x prime squared and multiplied with v of x prime. So this is just the interaction, which depends on the position of these two guys here. And then this U2 here, Hartree-Fock, this is actually the term which we call for the Fock term. And this is given by minus. And then we have a sum over all the states below the Fermi level. And we have a term here which goes like alpha prime, and then I have x prime, and then I have my Vx of x prime, and this is multiplied. And now you have to be careful because this alpha prime depends on x now. So what I've done now is to rewrite the Fock term in terms of these terms, x and x prime. And remember now that when you look back at the equations, what you have is that the unknown quantity you want to determine depends on x prime. And this has to do with the exchange property of the from the Pauli principle, which means again that we have a term here which looks like this. And this is the one we have to plug into the integral here. So what we are going to do now is simply to set up these equations and then make some transformations using Fourier transforms. We are going to Fourier transform to momentum space, and then we are going to have a recipe by which we can calculate these terms more easily. So these states which we have, this psi of alpha of x here, they are now given by some spatial path, and I'm going to introduce later the momentum, the linear momentum, and it's going to depend on r vector, and there's going to be a spin part here. So there will be a spin part where we have this one, and this is going to depend on this quantum number c here, whether this is spin up or spin down here. And we know that this spin part here, let me just write it in a more compact way here. We actually, the interaction we have does not depend on spin. So spin is just a degree of freedom which we can sum up. So this term here, if I write this one, this is going to be equal to the standard spinor 1, 0, in case the spin is equal to spin up, or it takes the value plus 1/2. So the sigma which you see here, sigma takes just the value 1/2. We are looking at the spin 1/2 objects, and this is the other one. So then we would just write it as some spin down, or it corresponds to a -1/2 here. And when I now look at the equations in coordinate space, I can, for the first term here, if you now look at the term which we have, the Hartree term, that contains a summation over the spins. So this alpha here sums also over the spin degrees of freedom. So we have to be a little bit careful, because alpha is a sum over all the states below the Fermi level. And these are states with specific quantum numbers k here, but they can also have spin up and spin down. And if you look at this specific sum which you have here, this sum here, the sum does not depend, so the potential does not depend on spin. So the potential which we have is going to be a potential x and x prime, which is actually equal to the relative distance, a function of the relative distance between two particles. Only that. There is no spin dependence. Which means then that since we have no spin dependence, when you look at this sum over alpha less than alpha f, this is going to be a sum over the spin values, which will now take the value plus 1/2 and minus 1/2. And then we have a sum of a spin over k less than kf here. So you can think of this k as another quantum number than spin. And in our case, we can now, in the sum which we have, we can actually sum freely over the spin degrees of freedom. So if we do that, then the Hartree-Fock equation can then be written out in the following way. So we have a minus h, the second derivative divided by 2m, and we have a term plus u of r, which also we haven't defined. So this is the charge from the background ions, and this is a potential which then confines the motion of the electrons. But we assume also that that potential is spin independent. And now if I look at my Hartree term, so I get plus, but then I get a factor of 2 because I'm summing over the spin degrees of freedom. And there is no spin dependence in the interaction, okay? So that means that what I have now is just a sum over these quantum numbers k up to the Fermi level, which I label as kf. And there is an integral over d over r. So no longer x, because x, the way I defined it earlier, was given by an integral over both spin, a sum of spins, and an integral over d over r. And then I have a state psi of k prime, and this contains an r prime squared. It's multiplied with the potential, which now depends only on r minus r prime. And then we multiply this one with a state psi of k, a psi of k. Let me just rewrite it here. So psi of k of r. And finally, I have the Fock term. And in the Fock term, actually, I have to be careful because the Fock term requires that we have the same spin values for particle 1 on the bra side and on the ket side. So that means that when we sum freely over the spins, there will be a factor which will be missing. So we will not get a factor of 2, but we will simply have a simple sum over k. So this should be k prime here. I forgot to put a prime here. And this is less than kf. And then I have my psi k of r. And then this is multiplied with the integral. And then I have my psi. Okay, this should be a psi actually. Psi of k prime. And I have a psi of k of r. And this is multiplied with v of r minus r prime. That one. This should be, let me just rewrite that one. And I'm going to use a shorthand here where I just write it as a function of r. No, not that one, not yet. Like this. And this one, so the factor of minus here, instead of a minus 2, is simply due to the fact that the spinos, which we are looking at, so let me just explain to you this in a little bit more detail. So when you're looking at the sum over the spins, so we have a spin, if we have 2 particles, we have a spin 1 and spin 2. And then we are having an integral over d of r1 over d of r2 when we are looking at specific matrix elements. And then we have psi of, let's call this alpha 1 of r1 complex conjugate. And this depends also on the spin value. So this depends as a spin function, which is sigma 1 complex conjugate. And then we have a psi of alpha 2 of r2 here. And then we have a spin part, which is sigma 2. This is multiplied with an interaction now, which depends only on the relative distance. And then we have a psi. So this would be the so-called Hartree term. And then we have a spin part of sigma 1 multiplied with psi alpha 2 of r2 and psi of sigma 2 here. So this is what we call as the Hartree term. And what we see now is that when we look at the spins, we see that this part here matches this part. They have to match each other. So if this one is a 1, 0, then this one has to be a 1, 0 when I'm now summing over the spins. So sigma 1, that sums over plus 1/2 and minus 1/2. So if sigma 1 is plus 1/2, then we have this specific state, which then we take the transpose of that one. So what it actually means is that we are, for that specific case, for particle 1, we have simply 1, 0, and 0, 1, no, and 1, 0. And we see that that is simply 1. So that is okay, right? If I have the next one with minus a half, then I have the next case, 0, 1, and 0, 1. And that's also equal to 1. So when I sum over the spins, since the interaction does not depend on the spins, I can sum up the spin degrees of freedom, and I'm going to get 1 here, and I'm going to have the same from sigma 2. So in total, I just get 2. Okay? That sound reasonable? Okay. So the if I take the Fock term on the other hand, if we do that, what we end up with then is that these this change. So for the Fock term, I would have a minus, and there's a sum over the spins, sigma 1 and sigma 2. I have the integral dr1, dr2 here, and then I have the same states here. And then this is multiplied with sigma 1, and then I have phi alpha 2 of R2, and then the spin part, sigma 2. And then I multiply this with a potential, which depends only on the relative distance, R1 minus R2 here. But then I have now a phi alpha 1 of R2, and then I have a similar one, sigma 2 here. So this will be particle 1. And then I have a phi of alpha 2, but now with R1. And then I have a psi here with sigma 1 here. So I have interchanged particle 1 and 2, and then I have to be careful with the spinors. And you will see immediately then, since the potential does not depend on the spin degrees of freedom, that you will only have a possibility when sigma 1 here, which you see here for particle 1, which we're now looking at where we have interchanged the quantum numbers, when sigma 1 is equal to sigma 2. So sigma 1 cannot differ from sigma 2. So that means that you will only get a case where you have both spins pointing up or both spins pointing down. These will be the only cases. So that will take away this factor of 2, which you had in front of the Hartree term. So that means that the Hartree-Fock equations will carry a factor of 2 here, and then you will have a factor of minus just 1 and multiply with that sum there. And this is something which you will often see in textbooks. We never include statements like we never include the spin degrees of freedom because they can be straightforwardly included later. But this actually gives rise to some minor confusion because we are not used to think of the spin degree. When you're not used to think of the spin degrees of freedom, suddenly you have to bake them in, and it's easy to make such small errors. You've probably seen often in textbooks, we easily see, oh, it's straightforward to include. So always be suspicious. I actually did that as an error when I was teaching modern physics. I had an exercise which I took from Landau and Lifshitz, where it said we can easily see that this is the result. And it took me a day to easily see or find the trick. And I came up with a trick right before the lecture. So we easily see. Okay, so so we must have the same spin factor, and what we end up with then, when we look at these equations, is actually this on the other page was an intermediate step. So if we just rewrite it like this is equal, and if we just skip this as an intermediate calculation, this is going to be equal to epsilon of k, and this is the Hartree-Fock term. And this is multiplied with psi of k and of r. So that set of operators defines the Hartree-Fock operators in the coordinate space. Now, when we now look at this charge from the background ions, this is something which we are going now to write, since we have a uniform set of ions. We are going to write this as E, which is the charge of the ions. There's an attractive charge, and there's a density of the ions, and this density is normally the wave function squared, and it's given by a d, so it has an r prime, or d of r prime, and this is divided by r minus r prime. So this is the ansatz we are going to make for that. And this density, which we have for the ions, has to equal the density of the electrons. So what we are requiring now is simply that this rho of r here is equal to the number of electrons divided by the volume which we have, times v. And since this is a charge density, it's going to have to be multiplied with the electric charge. So this potential which we have, this u of r, is simply going to be given by minus the number of electrons divided by v multiplied with e squared. And then we have a d of r prime divided by r minus r prime here. So that's the ansatz we're going to make for the distribution of this positive background charge, since it balances the charge which is set up from the electrons. What we are saying now is that this charge here has to be equal to the density of electrons multiplied with the charge. So it's a charge density what we have. Okay, so this is just an ansatz we are making about the model here. And now we are going to look at the setup of the Hartree-Fock equations. And we are now going to include the Coulomb interaction. And one of the things which we're going to use as an ansatz when we now look at the system, so we want the Hartree-Fock eigenfunctions or eigenenergies, or eigenfunctions and energies. And energies. So we are going to start with the first step, where we assume that we have no interaction. And in that case, we have simply kinetic energy divided by 2m here. And then we have this multiplied with psi of k of r. And this is given by some epsilon k, 0 here, just to indicate that we have 0 interaction, multiplied with psi of k of r. And we know that this is something we can solve, and you probably solve that using plane waves. I assume you see that in quantum mechanics or quantum physics. So I'm just going to state the solution here. So this is psi of k of r. It's something which we can normalize with respect to this volume. And these are just going to be given by plane waves. So I have k times r divided by the volume, the square root of the volume. And typically now, when you quantize this problem, so this is the particle in the box problem, right? With a potential with infinite volts. It's essentially that, it's the same problem. And then we know that these k's, they are actually quantized. And this k is now given by 2 pi divided by L. I'm just bringing back something you may have seen back in physics 2140 or quantum physics. And this contains now some quantum numbers, which we just call a quantum number of k with x. And this is multiplied with a unit vector in the x direction, plus an nky with a unit vector in the y direction, plus nkz for the unit vector in the z direction. And these numbers, nk, they take values from 0, plus minus 1, plus minus 2, etc. And this leads also to, for fermions, it leads also to a specific, shell structure, because you can fill in these orbits when nk is equal to 0. Then you have a specific energy, because then the energy would just be 0. The total energy of the system. When you put one of these equal to 1, then you can have a degeneracy here because you can have nkx equal to 1 and the two other ones 0. And then you just keep building this on, and you can fill in states with a given number of particles. And that defines a set of energy levels which are degenerate, because you would have, if you now have the next state above the ground state, then you can have one of these equal to 1 and the other ones equal to 0. And then you just keep building this up and up. Okay, so the next thing is actually to set up the energy. So actually this energy, when we put it up now, is given by this h bar squared multiplied with k squared divided by 2n. So I'm assuming that you've seen the solution of this problem before. So I'm just stating it here. Then the next step is actually to use the interaction. So now we add potentials. We add this u of r and v of r and r prime. Now the thing which is special here is that for this potential which we have, this v of r prime is actually a function which is translationally invariant. And there is something which I will just state here, and that is for an infinite system, the single particle wave functions which we have, which are the plane waves, are also eigenfunctions for the interacting case. So this translational invariant, and in an infinite system, the states which we have, this psi of k of r, with 1 divided by the volume of E of k times r, are also eigenfunctions, eigenstates for the Hartree-Fock calculations for HF, Hartree-Fock, of the interacting system. So I'm just stating that you can find proofs in many body texts on the electron gas, but I'm just going to use this state, this result. But this state which we have, but epsilon k 0 as we called, is not an eigenstate, or an eigenvalue. That's better to call it that. It's not an eigenvalue of the Hartree-Fock problem, of the Hartree-Fock Hamiltonian. So that means that we have to solve the Hartree-Fock problem for the energies, but we don't need to solve it for the eigenfunctions. So the eigenfunctions, the plane waves, are going to be the same for the interacting case as for the non-interacting case. But we need to set up the energy now. So what we are going to do next now, after the break, is actually to set up these calculations. So the next step now is actually solving the Hartree-Fock equations. So what we are going to show now is that we can solve these equations analytically. And that's extremely useful because we can then compare that with other many-body methods and see when we are setting up our calculations whether we actually get the analytical result. Because remember now that what we will be doing is to set up the calculations in the infinite limit. However, when you run a simulation numerically, if you run the Hartree-Fock equations for this specific case, you will always deal with a finite number of particles. And when you put particles in a box and you're setting up periodic boundary conditions, your results will depend on how you treat the boundaries. So having a Hartree-Fock calculation for the single particle energies is extremely useful when you are setting up your own machinery for solving such a problem. Okay, I went a little bit over time here. Let's take a small break, 15 minutes, and then we get back, and then we are going to run the calculation of the Hartree-Fock equations. So in order to solve the Hartree-Fock equations, there is an intermediate step which we need. And if we go back to the equations themselves, which we put up here, what we can do now when we put in the plane waves is to quickly realize that this term here is going to be equal to this term here, and they will cancel. So let's see how that comes through. So that's a small intermediate step which we need. And if we now set up the Hartree term, you will see that the calculations here are going to be much simpler. So let's do that one first. So we have a sum over the states below the Fermi level, and we have a K prime here. And these are now these discretized momenta, linear momenta. And we have a d of r prime, and this is now multiplied with these trial wave function which we put in, which are given by plane waves. And we know that if I plug in the plane waves here, this is just going to give us a volume factor, right? So if I put in here my psi of k prime of r prime, which is now equal to e of I of k prime times r prime, and I take the complex conjugate of that one, that gives me just the e minus kr, and then I have a volume term. So this becomes equal to 2 divided by the volume, and then I have a sum over k less than kf, and then I have my d of r of e squared, because I'm plugging in the Coulomb interaction here, divided by r minus r prime here. And in this specific case, what we end up with, when you now look at this term here, the volume term, the Coulomb interaction term does not depend on k. This just sums up over the number of particles. So this sums over particles. So that means that this becomes 2 times n and divided by v. And then I have a term here, which now is given by d of r. And then I get v of r minus r prime here. And actually this factor of 2, so this gives me a term which is going to be exactly the same as this potential which I had, times e squared here. And the factor of 2 here is actually going to disappear. So let me just take that one away. So that shouldn't be there. Because this state 2 which I have are the spin degrees of freedom. Remember that. So this one plus that one, yeah, that comes from the Coulomb interaction. So it's 2 charges, right? So it has an e squared. Yeah, yeah. And I'm skipping other terms here. So I've only kept the electric charge. But I should have kept the permittivity in vacuum and 1 over 4 pi, but I'm just skipping them. So you can think of this e squared as something which contains all these factors, okay? So keep in mind now that the factor of 2 is because of the spin degrees of freedom. So if you now have the states, suppose you have n particles is 8, so you could have k equal to 1, 2, 3, and 4, and that defines your Fermi level, kf. And then you have one state would spin up, one would spin down. And this could be now the system with 8 particles. So the factor of 2 is because you're summing over you have the spins already. And then you're simply summing over all the other states. So that means 2 times these other states is equal to the number of particles which you can have below the Fermi level. That sound okay? And this term here is nothing but the one which we put up for the attractive interaction from the ions. So which was given by this U of R from the background ion. From ions. Now, in this specific case, the 2 electrons repel each other. So you have a plus factor here, and that has to be equal minus the other one. So when you add the 2, they just disappear. So that means that the Hartree-Fock equations, which we have to solve now, are now going to be given by these plane waves. And what I'm going to do now is just to introduce the plane waves, and I'm going to calculate the Hartree-Fock energy. So what we had was a Hartree-Fock energy multiplied with a state. And if we multiply from the bra side of it, then what we get then, when we are setting things up, we will have a Hartree-Fock energy here. So this is the expectation value. And when we transform the kinetic energy to momentum space, we know that this one is given by h squared of k squared divided by 2m. That's the kinetic energy. And then I have the so-called Fock term. So I have a v squared because I have an interaction squared. And then I have a sum over k prime less than or equal than k of f. And this is now multiplied with an integral over d of r. And I'm now setting in the plane waves here, k minus k prime, and then multiplied with r. And then I have a new integral over d of r prime of e of I of k minus k prime. And then I have an r prime here. And this is divided by r minus r prime. So the only thing I did now was to plug in the plane waves, which we now, where we have used the fact that the interaction is translational invariant. So that means that these wave functions are also eigenstates of the Hartree-Fock solution. And what I did here was simply to take the expectation value of the energy. So I've actually multiplied. If you now look back at the equation we had originally, so we found that the term which we had here, this term cancels that one. And then we're just left with this term. And then I put in the plane waves, and I transform this one to momentum space, which gives me h squared times k squared divided by 2m. And then I multiply from the bra side with another plane wave here. And then I put everything together. And when I put everything together, I actually have these integrals, which you see here, to evaluate. And these integrals, I mean, what we need now in order to perform these integrations is actually to introduce a trick. And so we're going to introduce an additional convergence factor, which we then are going to let go to 1 in the limit of this convergence factor has a mu constant. So I'm going to, in order to solve this one, I'm going to introduce just a introduce a convergence factor in the equations, and then we're going to get rid of it later by taking the limit where this parameter goes to 0. So this is a common trick which is often used to solve this type of integrals. So we are going to calculate this quantity with this additional quantity here, this mu, and we're going to take the limit when we have performed the calculations, where we take the limit where this quantity mu goes to 0. So we are going to take mu goes to 0 after we've done the calculations. So when mu goes to 0, that means that we just have 1, right? But now I'm going to treat this mu as a finite quantity. And it's a standard trick which is often used in the evaluation of such integrals. There's another thing we're also going to do now is to actually use the fact that this 1 over v, and then when I have a sum over k, where the sum is limited to a specific value, this is something which you probably have seen before. It can actually be rewritten in terms of the density of states as an integral over dk. Have you seen, at least those of you who do solid state physics, you've probably seen this relation before. Anyone who has never seen it before? Okay, I can show you how you can get it afterwards. It's actually a very useful relation when you now assume that this volume becomes infinitely large. So that means that we can then replace the summation over k prime, which we have here, with an integral over k. So that means that what we have to evaluate then is the following integral. So we need the following, e divided by v squared, and this is now going to be given by, so I'm just putting in the sums which we had before, k prime, and then I have a d over r. So this is the object which is going to be more problematic to calculate, k minus k times r, and then I have my d over r prime of e of I of k minus k prime of r prime. And this is now going to be replaced by e squared divided by v multiplied with 2 pi cubed. And then I have an integral over d of r. And then I have an integral over d of r prime. And then I have r minus r prime, like this. And then I have now my terms, which go like e to the minus e of k of r minus r prime, multiplied with the next integral, which is dk prime of e of I of k prime of r minus r prime. And then I'm going to include this kind of convergence factor. So I'm going to replace this with a lim of mu goes to 0. And then I have e squared divided by v of 2 pi cubed. And then I have an integral over d of r. And then I have a d of r prime. And then dk prime. And this is multiplied with e of I of k. I always have to look at my notes when I write this now because it's so easy to actually make some small errors, of r minus r prime, and multiply with e of minus mu of r minus r prime divided by r minus r prime here. So this is the integral I want to evaluate, and I'm going to take the limit after I've evaluated the integral. So there are some tricks now which we are going to introduce, and then we're going to rewrite that integral, and let's now see where we end here. So it's not perhaps not the most exciting exercise, but it's actually useful to have seen this. So let's now introduce a change of variables. So I'm going to introduce an x, which is going to be given by r minus r prime. And then I'm going to introduce a new variable, which I call for y, which is simply r prime here. And then I can then rewrite that integral in terms of limit of mu goes to 0. And then I have this factor e squared divided by v of 2 pi cubed. And then I have my d of k prime. And then I have a d of y prime. which I'm going to write like this integral. So there's a k prime here. There's a d of x. And then I have e of I of k prime minus k times x, and multiplied with e of minus mu of x divided by the absolute value of x. Now, if I look at that integral which I have, the last one, so let's take a look at that one, because this is something which we can rewrite now. And I have an e of I of k minus k of x, and multiplied with the fudge factor or the convergence factor, and divided by this x. This is something when I open it up now and rewrite it in terms of the solid volume, this is something I can rewrite as an x squared of dx, and then I have the solid angle, d omega, which is then given by d theta sine theta and d phi. And just remember that that one gives us d phi of sine theta of d theta. So we can, that gives us two more variables, an integral of d phi and theta. And I can then rewrite this in terms of e to the I, and then I have my absolute value of k minus k prime. And this is then multiplied with x, the absolute value, multiplied with cosine of theta, and multiplied with e to the minus mu of x divided by x here, like that. So let's just wait a little bit till you have, because now I'm going to plug that into that integral. And I'm going to change variables again, because this x, the absolute value of x, is it's something I will rewrite as x. So if you do that, let's just look at this specific contribution. So we can, when we now replace x with x here, then I can rewrite what I have when I integrate away, because there's no dependence on the angle phi, and the angle phi goes from 0 to 2 pi. So I can rewrite this integral in terms of 2 pi, and then I have my x, and this is an x squared of dx of e of minus mu x divided by x, and then I have an integral from 0 to pi of d theta of sine theta multiplied with e of I, and then I have k prime minus k multiplied with x times cosine theta. And this is also something which I can manipulate further. And when I perform all these manipulations, what you will get is something like this. So you get a 2 pi of x squared dx of e of minus mu x divided by x. And then I can integrate from minus 1 to plus 1. So I'm just making a change of variables, because I know that cosine theta is the derivative of sine and vice versa, except for a sine. And then I can rewrite that in terms of an integral from minus 1 to plus 1 instead of 0 to pi. And then I have an integral over ei and then k prime minus k times x multiplied with gamma. So the only thing I did now was simply to perform the change where I know that d theta of sine theta, I replace that with a d of y, and y is simply equal to cosine theta, right? And then I know that since I'm changing this variable, I know that when cosine takes argument 0, then y is equal to 1. And when it takes value 2 pi, it's also equal to, it's equal to minus 1. It goes from minus 1 to plus 1. Okay, so the I can then recalculate with this trick here. And then I can, what I would get then, when I bring everything together, I get a 2 pi, and then I have a dx, x squared, divided by x squared. And then I have 2 times sine. So as I told you, this is not perhaps the most exciting thing we do. Times x. And I have e of minus mu times x divided by k minus k prime. Now, like this. And I can further rewrite this one since I have an x squared there and I have another x squared, so this just disappears, these two terms here. So that means that when I integrate up this one, what I'm going to get now is a 4 pi of mu plus k prime minus k squared. And you may have seen that result before. Okay, so that's the term which I get when I do that. So what I need to do now, the next thing, is to take the limit when mu goes to 0. Okay? And in the limit mu goes to 0 of this integral, I'm putting everything back now. I have v of 2 pi cubed. And then I have to multiply this one with the result which I have, because now I have an integral where this one goes up to the Fermi level, kf. And then I have a dk prime. And then I have an integral of a dy prime. And then I have my 4 pi divided by mu squared plus this term k minus k and squared. So what I'm going to do now is to replace the term. So remember now that this dy, there is no y dependence. So this term here defines the volume. So I can put that one outside because there's no y dependence. And that takes away one of the volume terms. So what I get then is that this becomes lim of mu goes to 0. And then I have an integral, which is going to be given by e squared divided by 2 pi squared when I put everything in. And then I have my integral over dk prime. And then I have my 1 divided by mu squared plus k prime minus k. And this is squared. And when I take the limit mu goes to 0, you see that there is no problem in taking that limit. And there is no dependence on the integrands except for this 1 over mu squared. So I can take that limit inside the integration sign. And that gives me simply now an equation which is given by e squared divided by 2 pi squared. And then I have an integral over dk prime divided by k prime minus k here. And that's the quantity which I have to evaluate. And this goes up to the Fermi level, because k is limited by that. And I can rewrite this one. Comes another trick here. So it's a tour de force in playing around with integrals. I have a sum over k squared of dk. So I should put a vector here because this is actually a three-dimensional integral. But now I put the value of the momentum for the Fermi level. And then I have a solid angle piece. There is no dependence on theta, but I have a sine theta here multiplied with 1 divided by, and I have the square root of, and then I have k prime squared plus k squared minus 2 times k vector, absolute value, k prime times cosine theta, like that. And this quantity here is the quantity now I want to evaluate, because this is also now squared, like that. And when I square it, the equation is going to be a little bit simpler. So there's a final exercise which we need to do now before we have the final answer. So let's go through the final details. And what we get then, when we put it in, we get an e squared divided by pi. We have an integral over k prime of dk prime. And then we have a new integral over 0 to pi. This goes from 0 up to the Fermi level. I have this integral here, which goes like d theta of sine theta. And this is divided with 1 over k prime squared plus k squared minus 2 times k prime, and then multiplied with cosine theta. And now I change variables. So I do cosine theta is equal to u as I did before. And then I get a new integral, which goes like e squared divided by pi, 0 to kf. And then I have my k squared prime dk prime. And now I have an integral from -1 to +1 due to the change of variables. I have a du, and this is multiplied with 1 over k squared plus k squared prime minus 2k prime times k, and this is times u. Now, this can then be calculated again. You will get a logarithmic function. And when we sum up everything, what we are going to get then is a new integral, which has to be integrated again. So we'll have a final integral here up to kf. And I'm going to get a k prime, a dk. And I'm just going to set up the final expression, which you get when you integrate up the last part. That will also have a factor of 1 over k prime. So it's going to be given by k plus k. And this is minus ln of k prime minus k. And this can be integrated up again, because we know how to integrate the ln of some argument k multiplied with k. So there is a final formula which we need at the end here. So let me just put that up. So we need now a new formula. So if we look at x of ln x, this is roughly what we have here. And we have limits a to b. We will then have 1 over half ln x of a to b minus 1/2 of the integral from x dx of a to b. So using that formula, we can then set up the final expression after some further manipulations. We are going to get that this final term gives us e divided by pi of k. And I'm going to get the Fermi level squared minus k squared divided by 2 times ln of kf plus k divided by kf minus k plus k times kf. And when I put everything together, what that means is that I'm going to get a Hartree-Fock energy, which now is given by h squared of k squared divided by 2m minus this term e squared of pi of k of kf squared minus k squared divided by 2 multiplied with ln of kf plus k divided by square root, no, the absolute value, plus k times kf. This is going to be the analytical expression for the Hartree-Fock energy. Now, there are interpretations which we are going to make of that, but we will put those interpretations in some of the exercises, which will come next week after the midterm. And we are going to look at the energy as a function of k, And we're also going to define the density of states around the Fermi level. And we're going to look at something which is also called the effective mass, which is a change to the mass of the particle due to correlations. So this is a concept which is often used in many body physics. So this is the Hartree-Fock energy. It's essentially just you playing around with different integral tricks, rewriting integrals. But the important thing is that we have an analytical expression for the Hartree-Fock energies. The next thing which we are going to look at is the calculation of the expectation value of the ground state. And that involves similar integral calculations as what we have here. So I'm going to state the result first, and then next time we are going to go through the derivation. But you will also find the derivation of it in the lecture notes. So let me bring quickly up the slides, and then we are going to, next week, we are going to look at the derivation of these terms in more detail. So the calculations which we went through here are also calculations which you will find in the as exercises here. And if you click on solution here, you will actually find it. Now, what we are going to look at next now is the calculation of the quantity which you see here, where you now can rephrase the expectation value of the ground state divided by the number of particles. So that's the energy per particle. You can rewrite that in terms of an analytical expression. And that's also something which is pretty unique. And this result, which you see here, both for the single particle energies and the Hartree-Fock expectation value for the ground state, is something which you then can compare with experimental data. And this RS is the radius of a sphere, which represents the volume per conducting electron. And it's often related to the Bohr radius, which many of you are familiar with from atomic physics. And it's common then to rewrite the energy in terms of the Bohr radius and the volume, which represents the conducting electron. And these are quantities which in solid, in metals, can actually be extracted from experimental data. And for most metals, you have a relation with this RS divided by A0, the Bohr radius, varies from 2 to 6. So this is a dimensionless quantity. And in the one of the exercises, so actually here we are going to go through these as exercises next week. But if we look at the ground state energy, what we need to look at now is to first obviously find an expression for the kinetic energy, and then we need an expression for the potential energy. And you will get the integrals which are similar to what you saw now. And if you take a look at these, so for the first part here, if you look at the two-body interaction, we need now to spell this out in terms of spin degrees of freedom as well. So the typical integrals which we end up with when we have plane waves, as we have put in here, are integrals where we need to evaluate something which looks like this. And we did parts of this already in this specific exercise, but now we are dealing with the integrals over particle 1 and particle 2 here. And we then need to set up the specific matrix elements with the plane waves. So we have the volume element here. We have the Kronecker deltas due to the spin degrees of freedom. And this ends up with, when we now look at the direct term, in this specific case, if this is a direct term, then we end up with an integral which looks like this. And this equation is something you will also find if you're dealing with the nuclear matter, which is I'm bringing this up as a small digression here, because nuclear matter is something which is widely used as well in order to simulate dense matter, like dense matter you find in neutron stars. And in that specific case, that is also a system where you have an infinity of neutrons and protons. So if you look at a neutron star, the expected number of neutrons and protons is something like 10 to the power of 57. So which we can essentially treat as an infinity. And the same type of calculations which you see here for the electron gas can also be used for nuclear matter. So what we need then, when we set up the Hamiltonian here, is to go through these calculational details which you see here. And this is what we will then go through next week. I haven't given you all the solution here, but we are going to set up some of the quantities. And for the kinetic energy, we will go through this calculation. And we are going to go through the calculation for the potential energy contribution. And when you go through all this algebra, you will end up with the equation which we announced, which is this equation here. So I'm going to go through some of these things next week. And then when we have that, we can use these contributions to the electron gas in order to define local density approximation in density functional theory. So, but we need to go through these technicalities first. And that's the topic for next Thursday. And then on Friday, we will say something about the link with density functional theory. But probably we'll begin with that on Thursday as well. So it's perhaps not the most exciting thing to run through all these kind of integral calculations, but sometimes it's useful to have seen the kind of tricks you can use to calculate some of these quantities. And this is where I plan to stop today, because this will require at least one part of the lecture next Thursday. But take a look at some of the slides here, and then I'm going to fill in more details when we meet next Thursday. And tomorrow, we will basically just discuss the midterm. We're not going to have a lecture then, but we just use the time we have for discussing the midterm. And don't hesitate to ask questions, and don't hesitate to ask whether the equations you get are correct or not. I mean, it's the insight which is the important thing, which you get from running these calculations. Okay, I'm going to stop here.